Okay, let's explore a really fascinating question today. What if planets aren't just, passively sitting there taking energy from their star?
Right.
What if they actually influence their host stars? Maybe even trigger some pretty destructive events.
It's a mind-bending idea, isn't it? And we're diving into some, well, truly groundbreaking new research that suggests exactly that. It kind of flips the script on how we usually think about these things.
Yeah, it really does seem to. So this is a deep dive based on some pretty serious observations, right?
Absolutely. Our insights today, they come from multiple space telescopes. We're talking James Webb, NASA's TESS satellite, and especially ESA's Cheops mission. It's all laid out in a recent paper in Nature, a team led by Ekaterina Eiflin.
Okay, got it.
Yeah.
So our mission for you listening today is to really unpack this incredible discovery. We want to get into the how and the why of it all.
And figure out what it means, for how we understand planetary systems in general.
Exactly. Get ready, because some of this is genuinely surprising stuff.
It really is. So let's meet the main players here. First up, the star, HIP 67522. And honestly, compared to this one, our sun looks kind of sleepy.
Sleepy. Okay, so it's a really active star then? That sounds pretty central to this whole story.
It is.
What are its characteristics? It's a bit bigger than the sun?
Yeah.
Cooler.
Yeah, slightly larger, a bit cooler, but the really crucial difference here is its age. It's incredibly young. We're talking just 17 million years old.
Wow, 17 million. Compared to our sun's, what, 4.5 billion years?
Exactly. It's a stellar toddler, basically. And that youth is absolutely key. It means it's highly active, it's rotating fast, lots of churning going on inside.
Which means stronger magnetic fields.
Precisely. It's a powerful generator of magnetic fields, much more dynamic than our older, more stable sun. And this high level of activity, well, it sets the stage for everything else.
Okay, so we have this volatile young star. What about the planet caught up in all this? HIP 67522b.
That's the one. It's the inner planet of two we know about orbiting this star. And its orbit is, well, astonishingly tight. It whips around the star in just 7 days.
7 days. That's incredibly close.
Yeah. When they first found it, it was actually the youngest known planet orbiting its star in under 10 days. But here's another really interesting, maybe crucial detail. Size-wise, it's like Jupiter.
Okay, a gas giant.
But its density, they describe it as like candy floss. It's incredibly low density, super puffy, one of the wispiest exoplanets we've ever found.
Candy's lost its density.
Yeah.
That sounds like it might be important later.
Yeah.
So this whole interaction, a planet triggering flares,
Yeah.
how did they actually catch it happening? I mean, wasn't this just theory before?
Well, yeah, astronomers have actually wondered about this since, like, the 90s. Could close-in planets mess with their stars' magnetic fields and set off flares? But this new study, this is the first time we've got direct evidence.
The smoking gun, so to speak.
Pretty much. And the journey to get there is quite cool. So initial hints came from telescopes like Webb and TESS. Then this team, led by Ekaterina Eiflin over at Astron in the Netherlands, they decided, okay, let's really dig into this with the latest telescope.
And TESS, that's one that does the wide surveys, right?
Right. TESS did a broad sweep, and when it looked at HIP 67522, the team thought, something looks interesting here. Something might be going on.
But they needed a closer look, to be sure.
Exactly. They needed more precision. So they turned to ESA's Cheops satellite, characterizing exoplanet satellite.
Ah, Cheops, known for its super precise targeting, right? On demand.
Yep. They requested time on Cheops, pointed it right at HIP 67522, and Cheops, well, it delivered the goods.
Okay, so what did Cheops actually see? What was the evidence?
It observed 15 distinct flares coming from the star. But here's the crucial part, the real clincher. Almost all of those flares happened right when the planet was transiting.
Transiting, meaning passing in front of the star from our viewpoint.
Right. Exactly. As seen from Earth, the planet crosses the star's face, and the flares popped off predominantly during that window. The timing, the correlation, it's incredibly strong. It really points to the planet being the trigger.
Wow. Okay. That's pretty compelling.
And get this, the flares themselves. They were about 100 times stronger than what earlier theories had predicted.
100 times. So this isn't just a little nudge.
No, it's a massive energy release apparently being set off by this planet.
That really does overturn things. We usually think of the star blasting the planet with energy, like, space weather, auroras on Earth, a one-way street.
Right. The assumption has always been that stars just do their thing independently. This study kind of throws a wrench in that.
So how? How does a little planet, even a Jupiter-sized one, trigger such huge flares on its star What's the mechanism they're proposing?
Okay, so the idea goes something like this. Because the planet's orbit is so incredibly tight and the star's magnetic field is so strong and dynamic.
Because it's young and active.
Exactly. The planet is close enough that it actually physically interacts with or disturbs the star's magnetic field lines. Imagine these lines looping out from the star.
Okay.
As the planet plows through this magnetic environment in its orbit, it somehow gathers energy, maybe through friction, maybe other interactions. The details are still a bit fuzzy.
Gathers energy, and then what? Sends it back.
Yeah, that's the idea. It sends this energy back towards the star in the form of waves traveling along those magnetic field lines. They compared it to snapping a rope and watching the wave travel down it.
Okay, like a disturbance traveling back to the source.
Precisely. And when these waves hit the ends of the magnetic field lines right back at the star's surface, they dump that energy, and that dump triggers the flare.
But you said the flares are way more powerful than predicted. How does that work? If the wave carries X amount of energy, how does it trigger a flare with 100x energy?
That's the really mind-blowing part. The researchers think the waves aren't providing all the energy for the flare itself. Instead, they're acting like a trigger, like a detonator.
So the energy's already there, waiting.
It seems so. The star is already magnetically charged up, maybe with these huge amounts of energy just waiting for a nudge. The wave from the planet arrives and basically sets off these explosions that are waiting to happen. It's like a tiny spark igniting a huge powder keg.
Wow, okay, that makes more sense, catalytic trigger. But hang on. If the planet is triggering flares, where are these flares directed?
That's the other kicker. It seems the planet is triggering them in its own direction.
Oh, no. So it's basically shooting itself in the foot. Or the atmospheric equivalent.
You could definitely say that. The result is the planet ends up getting blasted by about 6 times more radiation than it would if it wasn't triggering these flares.
6 times. And you mentioned earlier it has that candy floss density, right? A wispy atmosphere.
Yep. And being hit with all that extra high-energy radiation, well, it's really bad news for a planet like that. That radiation is actively stripping away its atmosphere.
Eroding it, so it's losing mass.
Much faster than we'd normally expect, yes. It's literally getting sandblasted by its own star, thanks to the flares it's helping to create.
So what's the long-term forecast for HIP 67522b then? Is it going to survive this?
While survive might be relative, the prediction is pretty dramatic over the next, say, 100 million years or so.
Which is not that long in cosmic terms.
Not really, no. It could shrink significantly. It might go from being this Jupiter-sized puffy giant down to something more like the size of Neptune, a much smaller, denser core left behind, perhaps.
A self-imposed downfall, as the paper put it. It's engineering its own demise.
That sums it up pretty well. A cosmic self-destruct sequence triggered by its interaction with its star.
Incredible. And you said this is the first direct evidence, so I imagine the lead researcher at Katerina Island, she must have more questions than answers right now.
Oh, absolutely. She literally said, I have a million questions because this is a completely new phenomenon, so the details are still not clear. This discovery just blows the doors open for future research.
So what are the next steps? What are the big questions they want to tackle now?
Well, a couple of key things. First, they want to observe these events in different wavelengths of light. Cheops saw them in visible and near infrared, but they want to look in, say, ultraviolet and X-rays, because those wavelengths carry a lot more energy and are particularly damaging to planetary atmospheres. Seeing those would tell us just how bad the sandblasting really is.
Right, get the full energy picture. What else?
The other big thing is, frankly, finding more examples. Is this HIP 67522 system a complete one-off weirdo? Or is this kind of planet-star interaction more common, especially around young, active stars?
So moving from one data point to a whole population study.
Exactly. If they can find, 10, maybe 100 similar systems, then the theorists can really get to work building much better models of how this all happens.
And it's pretty amazing that Cheops played such a key role here. Wasn't it mainly designed just to measure planet sizes accurately?
It was. Maximilian Gunther, the Cheops project scientist, even commented on that. He was excited that the mission is contributing to science so far beyond what it was envisioned to do. It's a testament to the instrument's precision.
And are there future missions that could take this even further?
Yeah, looking ahead, ESA's got another mission coming up called Plato. It's also an exoplanet hunter, and it's going to be looking at sun-like stars, including young ones like HIP 67522. The hope is Plato might be sensitive enough to catch even smaller flares, giving us even more detail on these interactions.
So much more to come on this, it sounds like.
Definitely, we've just scratched the surface.
Okay, so wrapping this deep dive up, What we've seen today is genuinely incredible. The whole idea that the relationship between a planet and its star isn't just one way.
Yeah, that a planet can be an active participant, actually influencing its star's behavior, even if it leads to its own pretty drastic transformation.
It really does shift how we think about star-planet dynamics. It makes you wonder, doesn't it? What other big assumptions we have in astronomy might get challenged as we get better observations?
Absolutely. And thinking about this specific planet, HIP 67522b, on its self-destructive path, how common is this kind of extreme interaction? Could it be a major factor in shaping how planetary systems actually evolve across the galaxy?
A provocative thought to leave you with. What are the rules of the cosmos that we think we know might turn out to have these really surprising exceptions just waiting to be discovered?
Makes you realize how much we still have to learn out there.